independent variable as a regressor. Usually that to explain the dependent variable. Now, how if your dependent variable have the same characteristic, meaning that your dependent variable is a binary. So just like a variable, so meaning that it's only contain or consists of two values, either 0 or 1. Okay, so we're going to discuss what's the alternative model you can use. So that is if let's say if we simply use the ordinary square, you simply regress that variable as dependent variables against other independent variables. The one we call as linear probability model or LPM. Again, so you can if you just simply regress as usual. Although your dependent variable is not a scale variable, but it is a dummy variable or binary variable. So if you do that, the model that model we call as a linear probability model. So the linear probability model uses OLS or ordinary square to estimate the model. The coefficient is I think extra and so on are then interpreted in the usual way. So the dependent variable has two values. The value 1 has a probability of P and the value 0 has the probability of 1 minus P. So this is known as the Bernoulli probability distribution. In this case, the expected value of a random variable following a Bernoulli distribution is probability the variable equals to 1. So basically, if our dependent variable equal to dummy variable, so basically we are interested to know what is the probability. The property, because the property is between 0 and 1, so basically we can use that to represent probability of getting certain things because the value we have either 0, just 0 or 1, so in between probability just take value between 0 and 1, so basically we can use that as a just like representing a probability. So since the probability of P must lie between 0 and 1, then the expected value of the dependent variable must also lie between 0 and 1. So, however, there are a number of problems if you simply regress the binary variable or dummy variable against other regressors using ordinary square. There are a number of problems involved. So the error term is not normally distributed. So it follows the Bernoulli distribution, which is meaning that it violates a number of assumptions for ordinary square. Okay, something that we discussed earlier. So the variance of the error term is heteroscedastic. The variance for the Bernoulli distribution is P1 minus P, where P is the probability of a success. And then the conventionally computed R squared statistic is of limited value in a dichotomous response model. Adjusted R squared not accurate. And possibly the most probability aspect of the linear probability model is the non-fulfillment of the requirement that the estimated value of the dependent variable lies between 0 and 1. So, because when we use our dependent variable is dummy variable 0 or 1. So we want the expected value must be either y hat fitted value or fitted value. Remember, the expected value means the fitted value the fitted. When you estimate, you get the y hat fitted value. So the expected value must be between 0 and 1. But when we use this model, when we regress the dummy variable against other regressor, then it's possible that our y hat fitted value is not in between 0 and 1, but it's possible that less than 0. Also, it's possible that the fitted value greater than 1. So one way around the problem is to assume that all values below 0 and above are actually 0 or 1 respectively. So to as a solution for this one, as a solution, if you get fitted value or printed value less than 0, then you just assume it is 0. If you get greater than 1, just assume it is 1. Okay, but it's not the best way. It's not what we call the good way of what we call that to model the probability. So an alternative and much better remedy to the problem is to use an alternative technique such as the logic of probability model. So in this lecture we discuss logic. Logic probably quite similar. It's more easier to do calculation of probability using logic or probabilistic model. The final problem with the LPM is that it is a linear model and assume that the probability of the dependent variable equaling 1 is linearly related to the x non-trivial variable. For example, if we have a model where the dependent variable takes the value of 1, if a mortgage is granted to a bank customer and 0 otherwise regress on the customer's incomes, the probability of being granted a mortgage will rise steadily at low income level but change hardly at all at high income level, meaning that it's no longer linear. So meaning that certain situation is not linear, but we assume it's linear, so meaning that it's not a proper model to model the probability. Alright, so logic model or logistic regression, both linear and logistic regression analyze relationship between multiple independent variable and a single dependent variable. So we still have one is our dependent variable. Linear regression requires a scale dependent variable. So normally we need our dependent variable using the linear ordinary square. So normally we need in order to fulfill the assumption that we discussed before, we need our dependent variable to be a scale instead of dummy variable scale. Okay, we have normal distribution, but logistic regression requires a binary dependent variable. That is a categorical variable with two categories, either 1 or 0 value. So logic is an estimation technique for equation with dummy dependent variable that avoid unboundedness problem of linear probability model, because the linear probability model that I mentioned just now is possible that our predicted value to be negative less than 0 or greater than 1. Okay, but the logistic provide an alternative that allow us to limit the value between 0 and 1. Okay, not outside, not less or not less than 0, not more than 1. So by using a variant of the cumulative logistic function, like dummy variable, the binary variable is coded 0 or 1 and indicate if a condition is or is not present, or if an event did or did not occur. So we assign 1, just like dummy variable. So dummy variable, let's say you have dummy variable to present male, for example, male and female, so you create a variable for male. So 1, if the event is present, so the condition is present, so which is if that person is male, then you put 1, if not you assign 0. So basically it's the same. So logistic regression uses independent variable to investigate the likelihood of occurrence of one of the categories of the dependent variable. Okay, so to estimate the likelihood of the occurrence of one of the categories, because we have two categories now, so 1 and 0. So logistic regression can use both scale and dummy variable as predictors. So logistic regression can use both scale and dummy variable as predictors. So in terms of the independent variable, we can use both. The scale means that numerical numbers and numbers, variables that represented by numbers, actual numbers. Okay. Dummy variable just 1 and 0. So dummy variable is a variable that we create. That's why we call dummy variable, because we create that variable to represent categorical things or what we call a qualitative aspect. So logistic regression requires binary dependent variable. However, for independent variables, we need it to be dummy, just like dummy variable or binary. It's only two values, 0 and 1 for the dependent variable. Binary variable indicate if a condition is present or absent. Logistic regression can also be useful when the dependent variable has more than two categories. For example, a variable that values the highest degree earned may have value 1 for high school, 2 bachelors, 3 masters, and 4 PhD. The variable can be recoded to a binary form. So instead of having 4 categories, then we recode to only have 2 categories, and then we use logistic regression. So to predict the likelihood of earning, so we encode only two categories, 0 for high school and 1 for bachelors, to predict the likelihood of earning at least a college degree. Even some scale variables can be recorded so that they take on binary form. One way of categorizing a scale variable is to indicate if each observation has a high value or a low value. So let's say you have income data representing income. So income is scale. Okay, income is scale variable, but you want to construct logistic regression to make prediction of getting someone to be high income or low income. So you can convert that income variable, the scale variable, to be a dummy variable by setting. So as you split the values into two. So you set if the value, those value greater than certain value, then to be in this one group, another less than that particular value to be in another group. So only two categories, two groups. Alright, so logistic regression predict likelihood which can be measured by probability, odds, or log odds. A probability is the ratio of the number of occurrences to the total number of possibilities. In contrast, the odd is the ratio of the number of occurrences to the number of non-occurrences. So there's a difference between, they are quite related, but they are not the same. So we have probability and odds. Okay, the odd ratio. Probability representing the number of occurrences over the total number of possibilities. Okay, but odd represent the number of occurrences against non-occurrence. So the following table shows the correspondence between some probabilities and odds. So let's say now we take an example. Let's say you toss a coin, for example, for 100 times. You toss a coin for 100 times. Then you are interested to what we call to examine the probability of getting hit. For example, when you toss a coin. Okay, so if let's say out of 100 times of when you toss the coin, so 0 hit, meaning that another 100 you get all 100 tails, tails 100, 0 hit. So in terms of probability, then is zero lah, probability. So number of getting hit 0 over 100 of the times you toss the what we call it, the coin. So in terms of probability is 0. Odds, number of occurrence 0 as well over non-occurrence 100, so the same lah, 0. But if let's say out of that 100, 10s are out of the 100, 10 of the outcomes hit, and then the rest, the remaining 90 tails. So in terms of probability getting hit, okay, probability of getting hit out of 100, okay, is 10%, 1 over 10. But odd, it is 1 over 9 because it is number of occurrence, which is 10, non-occurrence 90. So you see the difference, the difference between probability and odds. Probability, the number of the success, number of success over the total possibilities. That probability. Odds, the number of success over the non-success. Success over non-success. Yeah, that's the odd ratio. So you take another example. If 25 hit, so in terms of percentage of getting hit, it is 25%. Okay, but in terms of odd, it is 1/3, 1 over 3. 1 over 3. So you see another example like 50 in terms of probability, equal probability of getting hit and tails. But for the case of odd, it is equal to 1 because 50 hit, 50 tail. 50 hit over 50 tail, so it is equal to 1. So you see the difference. This one probability 50%, 0.5, but it's 1. So meaning that if the odds equal to 1, then equal probability of getting the two outcomes. So you see that the example, if 75 with this, 90 with this, and then 100. Okay. So probability range from 0 to 1, probability from 0 to 1, but for the case of odd, 0 to infinity. Whereas odd range from 0 to infinity. And odds of 1 means equal probability of occurrence and non-occurrence. And odd less than 1 means occurrence is less likely than a non-occurrence. So less than 1. So, and odds greater than 1 means, so greater than 1. If greater than 1 means that the non-occurrence is more likely to happen as compared to the occurrence. Okay, the non-success have more chance to occur as compared to the success. So the formula to convert odds to probabilities is given by this formula. So you can see that if you want to convert probability to be odd or odd probability, then you can use this formula. Probability equal to odds divided by 1 plus odds. This formula can be used to convert logistic regression output to predicted probabilities. Unfortunately, if we set up the model to predict the probability of occurrence directly, the coefficient would be too complicated to calculate or interpret. Luckily, there is a function of the probability that has a linear relationship with the independent variables. If we use this function of probability, the model has the exact same form as a linear regression model, and the coefficient are simple to calculate. So this function is a logic function, hence the name logistic regression, and also called the log odds function. Okay, so which is given by this term. So our dependent variable is log odds. Okay, the dependent variable it represents. So basically, all the regressors we have is explain the log odds. Okay, it predicts the log odds. Okay, natural log, the log odds. So or equal to this one also we call it as a logic. So we call it as a logistic or logic regression. The log odds is the natural logarithm of the odds of occurrence. The disadvantage is that the coefficients are on the log scale and a little trickier to interpret. Converting them back to their odds form makes it a bit easier to interpret. So this one, after you estimate the model, so the model gives you prediction of the log odds. So to get prediction of odds, you have to use anti-log. Okay, you have to convert log odds to be odd. How to convert? Using exponent lah. Okay, anti-log. Using exponent of this, you get estimate of or prediction of odds. Okay, so the AR statistic is comparable to the overall F-test of model significant regression. It is a test statistic for it's just like that. It is equivalent to F-test. Okay, this one we are testing all the model coefficient are 0 except intercept, and then alternative at least one of the coefficient is not 0. So basically, it's the test statistic calculated using this formula. So which is this one represents log likelihood from unrestricted model. This one for the restricted model. So the AR statistic has a chi-square with degree of freedom equal to number of explanatory variables. The null hypothesis is rejected if the test statistic greater than critical value from chi-square level. Or you also can just decide based on p-value. So if you use that, you provide p-value as well. So if p-value less than the significant level or far, then we reject the null hypothesis. And then we can use what hypothesis test, correlation test, just like how we performed that previously. Okay, for the case of normal regression. Alright, so consider the example. So let's say we have a binary dependent variable called as on gun. So it represents on in a gun or not. So we assign 0 if not, and you assign 1. So basically, if let's say you get data from survey data, for example, and asking the respondent whether they own a gun or not, and then we also ask their political views. Okay, and then we create a variable called as poll views. There is an ordinal variable, so a scale ranging from 1 to 7. So which is 1 represent as semi-liberal, so 2 liberal, 3 slightly liberal, 4 moderate, 5 slightly conservative, 6 conservative, and 7 extremely conservative. So basically here we want to predict probability of owning a gun based on the respondent political views, whether each of the level of the political views determines how it influences the probability of that particular person to own a gun. So for this bivariate example, we examine the influence of political views on gun ownership. The guiding hypothesis is that conservative people are more likely to own guns because political conservatives tend to support gun ownership rights. The likelihood ratio, if you so how to get that result, you go to you open this data example of this equation. So for the example, so we have, you notice that here we have own gun. So basically the original data is given in the SPSS data file. If you collect data through survey, for example, so later I will show you basically for the logistic regression, it is easier to make interpretation if we produce result using SPSS, instead of using A-views. But A-views also allow us to estimate the model. So this is own gun variable. So it is either 0 or 1. So 0 means do not own a gun, 1 own a gun. So we need that true survey lah. If we ask, we have a group of people, so we ask them whether they own a gun or not. If they answer no, we put 0. If they answer yes, we put 1. Okay, it's that variable. It's that normal variable. So some here for certain people we don't have, so it is a missing value lah. Yeah. So basically the same, and then we have political view as well. All views, so which is this is an ordinal variable. So we have 1 for semi-liberal, 2 for liberal, 3 for liberal, and so on. Okay. So we use the same number, the same value in the views. This one, so for the case of gun is now either 0 or 1. So many 0, only few 1. And then political views, so the same values, whether what the level of political views. Okay, between 1 to 7. Now to estimate the model in the views, you go to the linear probability model. The one that we explained earlier, we just if you use that method, we just simply regress as usual. You regress the old gun against all views using Oriented square. But there are, mentioned just now, there are a number of problems. Okay, and then the model not really does not specify the number of summation of the linear Oriented square or specific regression model. So we can use alternative. So this one, you go to quick estimate equation. So we have our independent variable, own gun, the gun ownership, whether they own a gun or not. And then we have an intercept, then we have political views, all views. So if you use this square, then it is the non-linear probability, it is linear probability model, the LPM. Okay, if you simply use this square, then it is LPM, linear probability model. But there are a number of problems involved when we simply use this square. Okay, this square. So alternatively, we use alternative to the linear probability model. You can use the logistic model. So you need to select binary. Binary. Okay, binary, then select logic. So I think in this lecture we just cover logic. So basically profit also almost, I mean, quite similar to the logic, but the way that we need to calculate probability or to calculate the estimated probability is more tedious as compared to logistic. So I think you just use one, just use logic. If you are interested to know about profit, then you can explore by yourself. So logic, logistic logic. Okay, so we get the estimate value. It's just like an estimate for the intercept, estimate for the slope for the whole particle views. Okay. So just now, so here we see that we have the AR statistic. So it's just like it's equivalent to the F test, okay. So but here because you only have one, so you want one regress. So basically it's supposed to be the same conclusion. So the likelihood ratio at chi-square of 41.4669 with a p-value of 0 tells us that our model as a whole is statistically significant. That is, it fits significantly better than a model with no predictors. So the result we obtained just now. The logistic regression coefficient have the same function as linear regression coefficient. They show the direction and strength of the relationship between the dependent and independent variables. In the above example, the direction is positive because we have the slope coefficient positive, 0.268. Okay, indicating that the more conservative a person is, the greater the likelihood of owning the gun. And then the slope coefficient represents the change in the log odds of the dependent variable for each one unique change in the independent variable. In this example, for every movement from one increment to the next towards the direction of increasing conservativeness on the political orientation scale, the log odds of gun ownership increased by 0.268. A more intuitive measurement of the strength is the odd ratio. The odd ratio, as explained earlier, so what I mean odd ratio, it is number of occurrence over non-occurrence, number of success over non-success, success over non-success. So the odd ratio is the coefficient with log removed because of the mathematical properties of log. It measures how many times higher the odds of occurrence are for each one unit increase in the independent variable. The odd ratio for all view is, you take exponent of this value, exponent of the estimated value 0.268, you take exponent of this, so you get, so this it gives you the odd ratio. Okay. So it is 1.307, you take an exponent of 0.268. Since it is greater than 1, then it means that a higher score, being more conservative, increases the odds of owning a gun. Okay, because this one greater than 1, remember, if equal 1, equal probability. If the odds ratio equal to 1, is equal probability for occurrence against non-occurrence. So if greater than 1, it is the chance of getting the success is higher than the non-success. Occurrence higher than, more likely to happen or more likely to occur as compared to the non-occurrence. Okay. So each one unit increase on the political view scale increases the odds of owning a gun by a factor of 1.307. People who consider themselves liberal with a score of 2 are 1.307 times as likely to own a gun as people who consider themselves extremely liberal with a score of 1. And then likewise, people who consider themselves slightly liberal with a score of 3 are 1.307 times as likely to own a gun as people who consider themselves liberal with a score of 2, and so on. So this one, I mean, later on when you see the table, then you'll be able to see what the meaning of this. What the meaning of 1.307? So meaning that the higher the level of the political views, and then it will increase. You multiply the odd ratio by 1.307. So for example, later on you see that this one, for the case of political view equal to 1, you get this one odd ratio, but you multiply 1.307, you get this. You get this, and so on. So each level multiply 1.327, you produce the odd ratio for the next level. So since the p-value 0, that is less than 5%, 0.05, we conclude that there is a significant relationship between political views and a gun ownership. Like linear regression, logistic regression coefficient can be used to make predictions based on a Brownian calculation. So you can calculate the fitted values as usual. So you have your y hat, just like y hat, equal to the estimated value for the intercept plus estimated value for the slope times that the regressor independent variable. But that one give prediction of log odds. It gives you prediction of log odds, not by odd, log odds. To get prediction of odd, when x equal to certain value, to get the prediction of odd, you have to anti-log this one using exponent. Okay, so again the fitted value represent the predicted log odds when x equal to certain value. Okay, so the predicted odds when x equal to certain value is the exponent of this. And then after you get this, you can convert odd to be probabilities. So once you know the odd, then you can calculate the probability. Again, using the formula given earlier. So after you calculate, you get this predicted odds, you can get the predicted probability by using the formula odds over 1 plus odd. Or if you based on the fitted value of based on the result of estimate, then you can use this one over 1 plus this, you get the estimate of probability. So example, if both views of political view equal to 1, so 1 means what? Just now 1 represent one for extremely liberal. So you want to know if that any person who is extremely liberal, what is their odds ratio of owning a gun, and then from there you can calculate the probability. So what is the probability of that person to own a gun? Okay, so you first need to calculate the fitted value when your variable, the ball view equal to 1, you calculate this one based on the estimated equation just now, the estimated model that we have just now. So this plus 0.268 times ball view. If ball view equal to 1, then you calculate, you get negative 1.477. Okay, that gives you estimated log odds. Okay, so you use anti-log using exponent. Exponent of this value gives you the estimate of odd ratio 0.2283. So this one, so 0.2283, and then you can convert this to the probability by using the formula that we discussed earlier. So this one divided by 1 plus this, so you get 0.18 by 9. So meaning that for those who are considered as extremely liberal, the probability of them to own a gun is just about 18.6%. Okay, the probability of them to own a gun equal to 18.6%. So if you do the same calculation for the case of higher level of political views, for those equal to 2 means that those are extremely liberal. So you replace the value, you do the same, you calculate, and then you get your probability equal to the odd ratio, you get 0.2985, and then using the formula, you get probability 0.2299. So you do the same for all level of political views. So you see this one, so meaning that for the highest level, the probability of, so you look at this one, up to level 6, okay, up to level 6, the odd ratio less than 1, so meaning that they are less likely to own a gun. Okay, this one, in terms of the probability also less than 0.5. Okay, so those are considered as extremely liberal until 6 conservative, slightly conservative. So they are less likely to own a gun in terms of probability of owning a gun. But those who are considered as the highest level, extremely conservative. So they have a higher chance of, they have a better, the greater possibility of owning a gun. They are more likely, so this one more than 1, the odds ratio more than 1. More likely to have to occur ownership of gun as compared to non-ownership of gun. Okay, so in terms of probability also 0.5 greater than more than half. We know the probability between 0 and 1, so more than half already. So more likely to own a gun. So the probability of an extremely liberal person owning a gun is 0.1859, and the probability of an extremely conservative person owning a gun is 0.5327. Now another example. Now if let's say we add more variables, so in addition to political views, we also add race, different race. So ordinally, okay, now this one, okay, this one, because this is ordinal political view, then we can just directly include that in our model. But if you have categorical variable like this one, so this one originally we have race, so race we have 3 different categories. So let's say this is your ordinal data. So in SPSS, let's say you collect data to survey, and then there are 3 different race: white, African American, and other. So you want to include that. You want to include this in your model in order to see whether the different race influence the probability of owning a gun. Okay. So, but this one you cannot directly include that variable. So you have this variable in SPSS, for example, you have this one. So you have this different value: 1 for white, 2 for African American, 3 for others. So if you want to run this in use, you have to convert this to be dummy variable. You cannot directly include this because this is categorical. Remember? So for the independent variable, ordinal, you can directly use that variable. But if you have categorical variable, you cannot directly use that variable. You have to convert to dummy variable. It's just like you have male, female. You cannot put 1 and 2 in the variable. You have to convert to be dummy variable because the variable, they present positive or categorical variable. So this one, if you have variable like this, categorical, then you have to convert. Okay, and use dummy variable. So because we have 3 categories, you have 3 categories here. Then you can include, if you have, remember, if you have normal intercept, then you can include up to 2 dummy variable for 2 categories. Okay, so if let's say in use, we create dummy variable, 2 dummy variable, 1 for, so basically we can create 3 lah, white. So dummy variable for white, we need that 0 if not white, 1 for white, and then African American, 1 if they are African, if not 0. And then others, if 1 if they are not white and African, with 1, 0 if others. But you cannot, if you have in the model, if you include C, you include the constant, then you cannot include all. That means, remember, just like what we discussed before. Otherwise, you have problem of perfect polarity. So if let's say in this case you exclude white, and you use that as your reference category, and then you include the other two lah as variable for African and other. Okay. And then another variable we have, so this one dummy variable for race, African as well as others, white as reference category. So you exclude white from the model. And then the third variable we have a socio-economic index, a scale variable with higher values indicating higher social status. So this one is just like normal variable, numerical values. This normal variable, it has numerical or we call it a scale variable, so we can just use that variable. You can include that variable in the model. Okay, so we re-estimate the model. Re-estimate. Where is the model? So you can just go to again quick estimate equation. So we have just now dependent variable on gun. And then C we have full views. And then we have African, others, and then we have SEI. So just, okay, don't forget I'm going to change to binary. Method binary, select, logic. Okay. So now you get this one. So you can see that we get for pole views we get slightly different estimate lah. But when we include more variables, and then you can interpret as before lah, similar to the one that we discussed before. So all of the variables except the socio-economic index (SEI) are statistically significant at 5% equal level. Because that one is 0.5 greater than 0.05. The rest are just 0 less than 0.05. The odd of gun ownership now slightly different. We get 1.27 because it is exponent of this. So it is, we can say that the gun ownership are 1.27 times higher for each one unit increase on the political views or pole view scale. The odd ratio reveals that African American are 0.286 times as likely to own a gun as white American. Why? Because white American is our reference category. So white is the reference category. So you compare to the reference category. And other minorities are 0.069 times higher. So given by exponent of this, as likely to own a gun as compared to white. So this one, for the case of African American, 0.2686 compared to white. So meaning that it is less likely lah. 0.26, its odd ratio less than 1, so it's less likely for the African American to own a gun compared to white. Okay. So similarly, for the case of other minorities, odd ratio 0.06, 0.09 less than 1. So again, they are also less likely to own a gun as compared to white American. So African American and other racial minorities are considerably less likely to own guns than white American, the reference category, since the weighted odd less than 1. And then the estimation results suggest that the odd of gun ownership for the case of ICI 0.998, so very close to 1 already. 2 times lower for each 1 unit increase on the socio-economic index However, if you inspect the coefficient, it's not significant because p value 0.5. Okay, so in terms of interpretation, we say there's no significant difference. Okay. Okay, so if you use SPSS, basically it's much easier. So if you use, you need to calculate the odds by taking exponent of this one. Okay, your exponent of this value, you get the estimate of the odd ratio. But if you use SPSS, you can directly get, it produce in the output, it gives you the estimated value of odds. So for example, this one, there are two benefits or two advantages of using SPSS for logistic regression. One, it calculates the odd ratio instead of you have to calculate manually. In EViews, you have to calculate manually. Now, okay, in EViews, you have to calculate manually the odd ratio. You have to use anti-log. And then another advantage of SPSS is that if you have critical variable like this, in EViews, you have to prepare your data variable first. You have to convert to be data variable. Let's say raise now 3 categories. You create a 2 data variable, you include. Okay. In the SPSS, no need to do that because you can tell SPSS that variable is a categorical variable, and then you can choose one of them to be a reference category. Okay. So in SPSS, what you can do, you go to analyze. So this one, we can just use the original variable. Don't need to convert to the dummy variable. You can just use the original variable. So 1 for white, 2 for African, 3 for other. You can just use the original variable. So you go to analyze, regression, binary logistic. Okay, so you choose your dependent variable. You own gun on a ship as your dependent variable. Your covariant is the risk and SEI. Now you have to tell SPSS that this race is categorical variable. You have to click categorical, and you put race in this box. Okay, and then let's say you use the first one as a reference category, meaning that now the first value 1 represent white. Okay, so meaning that the first one as the reference category. Continue, then okay. Continue, okay. So SPSS, we create a variable so that now, so we have the white. The full views I did actually have put full views. Oh, I haven't put regression. Shape for view I haven't put. For the views, you put for views SEI and arrays you tell that it's categorical. Okay, understand? Okay, I repeat. So this one is dependent variable, gun of the shape. So we have 3 independent variables now for views, race, SEI. But categorical. Race is categorical, so you have to tell that it's categorical. In just 1, 2, 3, so you have to tell the process that it is, the race is categorical, and you use the first value as reference category. So the first value, 1 for the white, okay, so we want it to be the same just like the one that produced by EViews just now. So continue. Okay. So we get this one. So you notice that we get the same estimate, but SPSS produce anti-log, and give us the estimated odd ratio. So no need to calculate manually, you can just get from here, the last column. Okay. Then exponent of the estimated coefficient. And then you can, there's another one model, that one we call it profit. So this one you can explore as one, but it is an alternative cumulative distribution function to that used in the logic model, in the normal CDF. When this used, we refer to it as the profit model. In many respects, this is very similar to the logic model. It is an estimation technique for equation with dummy with dependent variable that avoid unboundedness problem. So between 0 and 1, you have the same advantage as compared to the linear probability model. However, since logic and profit model generally give similar results, so here we just discuss the logic model, but you can explore. So if you use just now, then you can just select profit to estimate. But the way of to calculate the probability is more, I mentioned before, more tedious. If you select profit, then you get profit. But I think in this lecture we just cover the use of logistic logic model. Okay, so that's conclude this course. So meaning you have learned everything. If you learn, not everything. Maybe there are other method of regression that is not covered in this course. So if you want to learn more, then you can take another further geometry. But I want to be taught by different lecturers. I'm not teaching that course. Okay, regarding the quiz next week, so don't worry, it's very easy. How easy? It's very easy. You can just choose out of 4. This is multiple choice question. MCQ. So A, B, C, D. You just choose.
How many questions?
10 questions. So you will be given 1 hour. So maybe 1 hour for 10 questions should be long enough. So maybe next week we do revision first. We discuss because there is a request for answers for the midterm test. We discuss that one as well. We do a revision and then discuss answers for the midterm test. And then maybe the last 1 hour we use for the quiz. Okay, so 1 hour. So you can get it done in less than maybe 15 minutes. Even 1 minute can, just click. Tick. Can. Alright, so that's all for today. And then for your group assignment, remember next weekend, you need more time.